Hello there. You're very welcome to the fourth lesson of Dimensional Analysis chapter. I'm your own personal physics tutor, Dr. Rima McMullen. In this lecture, we're going to continue to work on problems of dimensional analysis, and you're going to see a variety of problems of varying difficulty level as well. So without any delay, let's start with problem number 1. So problem number 1 says, let the potential energy of a particle be given as, you're given this equation, U equals ax squared over x plus b. And we're told that x has dimensions of length. We're asked to determine the dimensions of a and b. Okay, so we know that on the left side, we have energy. What are the dimensions of energy? What's the dimensional formula for energy? Now, I have shown this in lecture number 2, so you can go and check it out there, or I'll just show it one more time over here. Now, energy is the ability to do work. That means energy and work have exact same dimensional formula. Now, if you remember, work is force times displacement times cosine of the angle theta between the force and the displacement. Do not worry about it if you don't understand it yet. We're going to work on it in very detail when the chapter on work comes around. So what I want to show you is that to get the dimensional formula for work, you will take the dimensional formula for each of these quantities on the right hand side and multiply them. Now cosine theta here, this is just a number. Cosine of 90 degrees is 0. Cosine of 0 degrees is 1. Cosine of 180 degrees is equal to -1, and so on. So cosine theta or any other trigonometric function with its angle, that's always going to be a dimensionless quantity. So do not worry about its dimensions. Dimensionless. Now looking at F. From Newton's second law, force equals mass times acceleration. And displacement, I'm just going to write d in parentheses for the dimensional formula for displacement. Taking it on, when I write out the dimensional formula for mass, I get m1. There is one mass. I'm writing down the dimensional formula for mass here. Times this L. There's no length here, so it's L to the power 0 times t to the power 0. Then acceleration. Acceleration's dimensional formula is m to the power 0, L to the power 1, t to the power -2. And the dimensional formula for displacement is m to the power 0, L to the power 1, t to the power 0. Now, if you want to know how I wrote down the acceleration's dimensional formula to be this, please check out lecture number 2 of dimensional analysis. There I have shown how this comes. Okay, now what I'm going to do is, here m times this m times this m. Bases are same. When you're multiplying quantities with same base, what do you do to the exponent? You just add their exponents. So this will give me m to the power. This 1 plus this 0 plus this 0. Now adding 0 gives us nothing. So this will remain m to the power 1. Now I see that this one looks kind of funky, so let me fix it. M to the power 1. Next we'll move on to L. L to the power 0 plus this 1 plus this one over here gives you 2. T. T to the power 0 -2 and 0. 0 -2, 0. Add them up and you will get -2. So here is the dimensional formula for work or for energy, because the dimensional formula for work and energy is the same. Why? Because energy is the ability to do work. Okay, so let me now rewrite this equation. It says the potential energy of the particle is equal to ax squared divided by x plus b. Now I know that the left hand side is m to the power 1, L to the power 2, and t to the power -2. On the right hand side, I have the dimensional formula for A, dimensional formula for x squared, and dimensional formula for x plus b here. Why? Because x plus b, now it's an expression, okay? While at the top, a and x are being multiplied. So there is this difference, okay? And if you remember the principle of homogeneity, it says that you can add or subtract only those terms that have same dimensions. So now here, okay, I'll write this down. Can add or subtract. Now, really, technically speaking, subtraction is kind of addition. Do you agree with me? Let me know in the comments, how is subtraction a kind of addition? All right, back to the principle of homogeneity. You can add or subtract only those terms that have the same dimensions or units. Or you can say units here. That means the dimension of B is same as the dimensions of X. And what did we say the dimensions of X are? We're told that in the problem. We're told that X has the dimensions of length. So that means X is M0, L1, T0. So this is the dimension or the dimensional formula for B. So what I will do now is, okay, let me put a line here. Here we go. All right, good enough. I'm going to here write down A, I do not know yet. Then we have this x squared. Its dimensional formula will be m0 L2. Where does this L2 come from? This x squared over here. We're told that x has dimensions of length. And in the dimensional formula for length, L is the only one with the non-zero exponent. So if I had m0 L1 T0 to the power 2, that will give you this thing over here, okay? Divided by m0 L1 T0. Okay. Now, what do we get here? We get dimensional formula for A times m to the power 0 divided by m to the power 0 still remains m to the power 0. Next, L to the power 2 divided by L to the power 1 gives you L to the power 2 minus 1. T to the power 0 divided by T to the power 0 is still T to the power 0. This gives us dimensional formula for A times m to the power 0, L to the power 1, T to the power 0. What do I have on the left-hand side? I have m to the power 1, L to the power 2, T to the power minus 2. Now on the right-hand side, I want the dimensional formula of A, which is A in parentheses by itself. So that means if I divide both sides of the equation by this thing here, this dimensional formula, M0, L1, T0, then I can get rid of these terms on the right-hand side. Whatever I do on one hand side, I have to do it on the other side as well, or the equation will not stay balanced. So what does this give me? This gives me dimensional formula for A equals m to the power 1 and 0 gives 1. L to the power 2 and this 1 gives you 2 minus 1. T to the power minus 2 and this 0 stays minus 2. So let me swap left and right side. That makes no difference. We get m1, L1, T minus 2. So we say that this is the dimensional formula for A. We are asked to find the dimensions of A and B. So from here, I can say dimensions of B equals 0, 1, 0, 0, 1, 0. And dimensions of A are 1, 1, minus 2. Now 1, 1, minus 2. What else is this dimension of? This is dimension of something else as well. Go for the shortest solution. Take the path of least resistance. Why? Because the fewer the number of steps, the easier the solution is, the less likely you are to make a mistake. So, that was an advice I was given many years ago by one of my own professors. Okay, so we're given this formula, right? We know that. Now doing it using units. Here, another solution. Using units. What's the unit on the left-hand side? Energy is measured in joules, J. I want to know the units of A. So how about, let me put this A in box, implying that I'm trying to find the units of A. Unit of X is meter square. B plus X, this is one term. Here each term has same unit. So you're not going to get here meter plus meter or meter times meter at the bottom. You're going to get just 1 meter. Why? Because X and B, they have the same dimensions. Okay, hopefully you understand that. M cancels out one of the M's at the top. What are we left with? On the left side, joules. On the right side, here we have the A in the box, which implies that we're trying to figure out the dimensions of A. This is the dimensions of A. Now the dimensions of A becomes J over M. What is J? This is newtons times meter over meter. Meter cancels out, equals newtons. So here, this was very easy. Right away, when you see that B is here being added to X, you know that whatever is the dimensions of B is the dimensions of X. Okay? Then, if you didn't want to do even that much, you could have said, okay, so here U equals AX squared divided by B plus X. Now, this is not technically correct, but I can say that this is kind of like this. I mean, B plus X, I call it just X. It's just length. Then this X cancels out one of these. So here, this X is implying just length. It doesn't have a value there. So I'm left with AX equals U. So A is equal to U over X. Joules over meters, which gives us newtons. And newtons will have dimensional formula 1, 1, F. It has dimensions 1, 1, minus 2. In other words, it has dimensional formula M1L1T minus 2. And from here, it was very easy to tell the dimensional formula for B. It's just that of length. I hope that it made sense. If you have any questions, any concerns, if you think that something could be done differently in any way that will make it better, please let me know in the comments, and I promise I'll read your comments. Okay. Hopefully this was clear. Let's move on to problem number 2 now. Let's see. You will see that this happens to also be the dimensions of force. Now, did I really have to do this elaborate work? If you're taking an exam where every second counts, you need to really know the shortcut methods. Problem number 2 gives us the force of interaction between two atoms is approximated by the following equation. I'll write down this equation: alpha times beta times exponential negative x squared over alpha kbt. Here x has units of length, k sub b is Boltzmann constant, and T is the temperature. We are asked to find the dimensions of alpha and beta. Okay. Now, let's solve it using units. Why? Because it makes your life really easy. So let's solve it using units. What does that mean? What is the SI unit of force? Newtons. SI unit of alpha, we don't know. This is the SI unit of alpha. Let's put it in a box. SI unit of beta, put it in a box. This, putting alpha in a box, beta in a box. This implies that this represents the unit, SI unit of alpha and SI unit of beta. I just made this up. Exponential minus x squared over alpha kbt, the SI units of this thing. Okay, so box is representing the SI unit. Have you ever seen it done this way before? I have not. I just made this up. Okay, I hope you get it. Now, here is an important point. This exponential, whatever is the argument here, this thing is called as the argument. This has to be just a number, plain number. It has to be dimensionless. If it is dimensionless, means it has no units. Means that the units of x squared over alpha kbt cancel out to give you 1. These are the units. Okay. So put unit of x squared divided by unit of alpha divided by unit of kb and t. They will all cancel each other out. So let's see how this plays out. Okay, so unit of SI units. Let's write down SI units. X squared, we're told that it is length. So it's going to be meters squared. SI unit of alpha, I do not know, so I put it in a box. Now kBT, this is the average energy of a gas. Okay, so the SI unit of kBT is going to be that of energy, which is joule. And this should be equal to 1. Okay. Go ahead and multiply both sides of the equation by this SI unit of alpha, which I'm representing by alpha in a box. What this does is, it cancels out alphas on the left-hand side. What am I left with now? Let me swap left and right sides. That gives me alpha equals meter squared over joule. Now what is joule equal to? Joule equals newtons times meter. Okay? What this does is this cancels out one of the meters at the top. What do I have now? Meter divided by newtons. Okay. Now this meter divided by Newton. Newton equals kilograms times meters per second square. That's what 1 Newton equals. Now this further cancels out this meter. What am I left with? This second square goes upstairs, becomes second square divided by this kilogram. How the second square goes up? Denominator of the denominator is written like this. It's actually the numerator. Denominator, this denominator of the denominator is the numerator. Okay. So I got the SI unit of alpha to be second square over kilograms. Coming back to the problem. Newton equals SI unit of alpha times SI unit of beta. And times this thing, this was dimensionless. So we do not need to worry about this. What do we get next? Alpha, we just figured it out to be what? Second square over kg. That's the SI unit of alpha. Second squared over kilograms times this beta equals newtons. Okay. So that gives us that the SI unit of beta is newtons times kilograms over second squared. Now we are asked to figure out the dimensions of alpha and beta. To determine the dimensions of something, you must have these units put in the most fundamental units form. And the most fundamental units belong to the most fundamental physical quantities, which are mass, length, and time. So Newton, I'm going to write this Newton as kilograms times meters per second square times this kilogram. Let me use yellow here. This kilogram divided by the second square. What does this give me? This gives me kilograms times kilograms is kilograms square meter times s square. S square gives you s to the power -4. So this gives me that the dimensional formula of beta equals here m for this kilograms squared. This is meters, gives you L to the power 1 times T to the power -4. Done. And alpha was second square over kg squared times kilograms inverse, which is same as kg inverse times meter to the power 0 times second square. Okay, this will give us the dimensional formula for alpha to be meter This gives the dimensional formula of alpha to be mass to the power -1, length to the power 0, and time to the power 2. So from this, we have the dimensions of beta and alpha. Dimensions of beta are 2, 1, -4. And dimensions of alpha are -1, 0, 2. So we know that the dimensions of alpha times beta should give us force, correct? We knew that from here, over here. So let's go ahead and multiply them out and see if we get the right thing. M2L1T -4. This is beta times alpha. M-1L0T2. What does this give us? M to the power 2 minus 1 is 1. L to the power 1 plus 0 is 1. T to the power -4 plus 2 is -2. And indeed, this is the dimensional formula for force. So we have calculated alpha and beta correctly. Okay. If you want to check it further, you can insert this back here. X squared over alpha kbt. Basically, we're going around in circles here. But it's always good to double check your answer if you can. So I'm going to drop out unnecessary L's, T's, M's. You will see what I mean when I solve this problem here now. X squared, I'm not going to write M0 here. I'll write just L squared. I'm not going to write T either. Divided by dimensional formula for alpha, and this kBT is the energy. And energy is M1 L2 T -2. Okay. So this gives me, if I want this to be equal to 1, that means alpha will have to be L squared divided by M1 L2 T -2, which gives us, this L squared kind of cancels out. I'm left with M1 T -2, which is T squared over M, right? And if you look at the units of this is going to be second squared over kilograms. And that's precisely what we have up here. Over here. So I know what I'm showing you is, if you would do it, like if you're asked to solve a homework problem or show a complete solution on a test, and you did this thing, yeah, you will lose a whole chunk of points. Because really, just writing L squared is not correct. But if you're taking a test, do this. This is much quicker. So learn all the different ways of approaching a problem. Difficult ways, easy ways, medium ways. And depending on the situation, you can try whichever way, is the path of least resistance on a test. And sometimes you might want to check your answer. You might want to double check your answer. Then you can try solving it using different approaches and see if the answer matches in all of those approaches. Now we obtained the units of alpha. to be second squared over kilograms, which can be written as second squared times kilograms inverse, which is same as kg inverse times meter to the power 0 times second squared. Problem number 3 says, for the following equation, determine the dimensions of alpha and beta. And the equation is x equals alpha a tau. So this symbol here, this is again another Greek symbol. It is called as tau. So x equals alpha a tau plus beta tau squared. Here x has dimensions of length, a has dimensions of acceleration, and the tau has dimensions of time. We are asked to determine dimensions of alpha and beta. Alrighty? So let's rewrite the equation. X equals alpha a tau plus beta tau squared. Okay. We're told that x, it has dimensions of length. So on the left-hand side, we have m0, L1, T0. This is the dimensional formula for length. On the right-hand side, we're asked to determine the dimensions of alpha. So let's write dimensional formula for alpha times dimensional formula for a, the acceleration, times the dimensional formula of tau, the time, plus we're asked to determine the dimensional formula for beta. So here's the dimensional formula for beta times the dimensional formula for tau squared. Okay, so let's focus on the right-hand side for now. We get dimensional formula for alpha that we're trying to determine times the dimensional formula for acceleration is m0, L1, t minus 2. And I have shown this in the second lecture, just in case if there is anybody who doesn't know how the dimensional formula of A comes. Please review my lecture number 2. Tau, dimensional formula for tau is m0, L0, t1. Then I have the dimensional formula for beta times the dimensional formula for tau squared, which gives us m0, L0, t to the power 2. And on the left-hand side, I have m0, L1, t0. Now, from the principle of homogeneity, the dimensions of each of these three terms, so see, there are these three terms. There's one term to the left side of the equal sign, and then there are two terms on the right-hand side. These two terms on the right-hand side, they are separated by this equal sign, this plus sign here, okay? Now, from principle of homogeneity, the dimensions of 1, this T1, first term, T2, and T3, these dimensions are the same. So I'm going to use this principle, the principle of homogeneity, to solve for the dimensional formula of alpha and of beta. Let's try to solve for alpha first. M0, L1, T0 is the dimensional formula on the left-hand side. On the right-hand side, I have dimensional formula of alpha times. Now I'm going to multiply these two. M to the power 0 times m to the power 0 is going to remain m to the power 0. Next is L to the power 1 times L to the power 0 gives us L to the power 1 plus 0 is still 1. Last I have t to the power minus 2 times t to the power 1. That gives us t to the power minus 2 plus 1. Carrying on, plus, let's now figure out this side. There's nothing to figure out. Let's just keep it the way it is. M0, L0, T2. Okay, let's very quickly rewrite this thing so we can combine these two powers of T. M to the power 0, L1, T minus 1, plus dimensional formula of beta M0 L0 T2. Okay, now we just said that the dimensional formula of T1 equals dimensional formula of T2. So that's exactly what I'm going to do. I'm going to equate T1 with T2. What did I say T1 is? T1 is the left-hand side of the equation, M0 L1 T0. And T2 is dimensional formula of alpha times here, M0 L1 T minus 1. Now I want the dimensional formula for alpha. That means we want to isolate alpha. We want alpha all by itself and nothing with it. So to get rid of whatever is multiplying alpha, we are going to divide it by this thing that multiplies alpha, M0 L1 T minus 1. But if you divide on one side, you have to divide on the other side of the equation. So here we get, on the other side, divided by M0 L1 T minus 1. So right-hand side isolates alpha, and on the left-hand side, we'll get m to the power 0 divided by m to the power 0 still remains m to the power 0. L to the power 1 divided by L to the power 1 is L to the power 0. T to the power 0 divided by T to the power minus 1 gives you T to the power 1. Okay, so that's my alpha. Now to solve for beta, I'm going to use the same principle. Let's set T1 equal to T3. T1 is the left-hand side, which is M0, L1, T0. And what is T3? We called T3 as beta times M0, L0, T2. So this gives us beta times, this is beta, M0, L0, T2. Now to isolate beta, divide both sides of this equation by M0, L0, T2. This cancels out everything except beta on the right-hand side. And on the left-hand side, we get M0 divided by M0 is M0, L1 divided by L0 is L1, and L0 divided by, T0 divided by T2 is T to the power minus 2. This is the dimensional formula for beta. So this has dimensions of acceleration. How so? If you don't see how these are the dimensions or the dimensional formula for acceleration, if you don't see yet how this is dimensional formula for acceleration, please watch lecture number 2 of this chapter and you will see how to obtain the dimensional formula for acceleration. So here, this problem is done. We got the dimensional formula for alpha, which is M0, L0, T1. This has dimensions of time. And the dimensional formula for beta, which is M0, L1, T to the negative 2, which is the dimensions of acceleration. So there you go. This was problem number 3. Moving on to problem number 4. For problem number 4, a dimensionless quantity m is expressed as, this equation. Here x has dimensions of length, T is the temperature, and Kb is the Boltzmann constant. Determine the dimensions of A. What's the equation? M equals A over B, natural log of Kb T over Bx. Now what are we told? That M is a dimensionless quantity. That means it is also unitless. So that means dimensions of M, which is none really, it's going to be M0, L0, T0, or you can say there's no unit. is equal to dimensions of A, or dimensional formula of A over B. Now, this is very important here. Natural log of anything is just a number. That means this argument here, the units of the argument cancels out, or the dimensions of the argument cancels out. That means kbt over bx. If I put in the units or the dimensional formula of these things, this will give me 1. This is a very important point. Now, in order to determine the dimensional formula or dimensions of A, I have to know dimensional formula for B. And where would I get that from? From over here. So kbt, just put in the units. Joules. B's units, I do not know. X's unit, just meter, equals 1. From here, okay, multiply both sides by the B inside the box. So what happens? This B's cancel out on the left-hand side, and I get this B in the box equals joules per meter. Okay, so I got the SI unit for B, joules per meter. I know that joule is equal to M1L2T minus 2 divided by meters, M0L1T0 gives me M1L1, okay, that doesn't look like L. L1T minus 2. This happens to be force actually. Okay, so now here we can write M0, L0, T0 on the left-hand side equals A divided by M1, L1, T minus 2. So this really is just 1 here. So multiply both sides by this denominator here. What does that give you? SI units of A equals M1, L1, T minus 2, which is force. So dimensions of A are 1, 1, minus 2. So if you really wanted, you could have done M equals A over B, right? Now B, I said, is equal to joules per meter. So this is 1 here. If I'm writing in terms of units, there's no unit, okay? So that means if this is 1, then the unit of A must be equal to unit of B. Unit of A equals unit of B. In other words, dimensional formula of A equals dimensional formula of B. So once you know B from here, you just know A, right? It was that simple. It looks deceptively harder than it is. That's how they like to make these problems on the test. They like to make it look hard, but they're not really that hard once you get them. I hope you get it. Okay. Alrighty. Moving on to problem number 5 now. And I think I'm going to make it a little bitty harder than this. Problem number 5 says the work done by a gas molecule in a combustion engine is given by the following expression. And here in this equation, just like before, x is the displacement and uppercase T is the temperature. And K sub B is Boltzmann constant. So do you see any similarity between this problem and the previous? Actually, I do. In the previous problem, you had M here, and you had something over here, and another exponential. So you had like either A over B or A times B, something like that. Let's say it was A over B. And B was given over here in the exponential. So what you did was you found out the dimensions of B from the exponential, plug that in here, and solve for A, because you knew that the dimensions of M were 0. Okay, so now in this problem, we have a very similar case. So I suggest that pause this video and try this on your own. Try the problems on your own. The second lecture of these problems In other words, the lecture number 4 of the dimensional analysis chapter. These problems are still relatively easier. In the next lecture, I'm going to get some more, tougher problems than these ones over here. Anyway, for now, I know, or we know, that exponential, which is minus bx squared over kbt, is dimensionless. Okay, so what does that tell me? That tells me this exponent. Now, I can write it whichever way. Okay. I can write it kbt over bx squared or bx squared over kbt. Okay. It doesn't matter. If I write down the units of these or dimensions, what would I get? 1. So let's go ahead and use units here. Unit of b, we do not know. Unit of x squared, meter squared. Unit of kbt, joule. This equals 1. Alrighty. Go ahead and multiply both sides of this equation by what? Multiply by joules, okay? Divide by meter squared. What does this do to this equation? Meter square cancels meter square. Joules cancel out joules. What do I have left here on the left-hand side? B in the box. What does this B in the box mean? This is my way of saying that I mean dimensions of, the units of B. This equals joules over meter square. Now, I'm not going to leave it just like this. Actually, for this case, maybe I should. Why? In this case, it will be more useful to leave it like this than to convert it into the units of the fundamental quantities, mass, length, and time. Why? You will see in a second. Now, the given equation is W, the work done, equals a squared times b times exponential minus bx squared over kbt. Now, when I write in terms of the units, I can totally disregard that I have this factor over here. This does not matter, okay, when I write down the units of the whole equation. On the left-hand side, I have joules for work. A squared, I want its units. B equals joules per meter squared. Okay. Now, go ahead and divide both sides by joules. Go ahead and multiply both sides by meter squared. So what that does is on the right-hand side, joules cancels joules. And it turns out that even on the left-hand side, joules will cancel joules. On the right side, though, I'll have these meter square cancels meter square. So what do I have left? This a squared equals meter square. So this a square is area. If you were to write down the dimensional formula for a squared, it will be m0 L2 T0. What are the dimensions of a squared? 0, 2, 0. But are we asked for the dimensions of a squared or a? We're asked for the dimensional formula for a. Okay. So we have this a squared, its dimensional formula equals m0 L2 T0. Now what I can do is I can write this as this. Similarly, I can factor out this power of 2 on the right-hand side as well. Now go ahead and take the square root on both sides. And that will give you the dimensional formula for A equal to M0 L1 T0. And there, you're done. That's what the problem asks you to do. You got it. There it is. We got it. That was our problem number 4. All right, moving on to problem number 6. That's going to be a tricky one. Problem number 6. It says, considering the universal gravitational constant g, the speed of light c, and the Planck's constant h as the fundamental physical quantities, the time period will have which of the following dependence? Quite interesting, huh? So, universal gravitational constant. Let's see what that is equal to. Now, Newton's law of gravity that we have all heard about, right? Is there anybody here watching this video who hasn't heard of Newton's law of gravity? Everybody has. So let's say you have a mass m1 and a mass m2, and their center of masses are separated by a distance r. They will each exert a force of gravity on the other, and that force will be proportional to the product of their masses, and it's proportional to the inverse square of the distance between their center of masses. And it turns out when we take away the symbol of proportionality, we introduce a constant of proportionality, uppercase g. Now, uppercase g and lowercase g mean two very different things in physics. So you cannot use uppercase g for lowercase g or vice versa. Okay. Now we're told that take this g as the fundamental physical quantity. So let me solve for this g here. So what you do to solve for g, you want to isolate g. Multiply both sides by r squared. What does that do? Gets rid of r squared on the right hand side. But here, g still has this m1 and m2 multiplied with it. So go ahead and divide both sides by m1, m2. Here. So this cancels out m1, m1, m2, m2 and gives us g equal to what? This thing. F times r squared divided by m1, m2. Okay. So we really want to figure out g in the real most fundamental quantities, which are really mass, length, and time. Now we know that force, this is in newtons. Okay, let's write down the units of g. And SI units. Okay, newtons times meter square over kilograms squared. So what is Newton equal to? Newton is kilograms times meters per second squared. This is just the Newton, okay? Then I have this meter square. And divided by, I have this kilogram squared. What does this give us? Kilogram cancels one of the kilograms here. I have now at the top meters cubed divided by kilograms second square. So the dimensional formula of G is mass inverse length cubed time minus 2. You see that? From here. Kilograms comes upstairs, becomes minus 1. Meter cubed stays upstairs, and second square comes upstairs, becomes negative 2. Okay. Now we might as well figure out let me write it here. Minus 1, 3, minus 2. Dimensions of G. Minus 1, 2, minus 3. Is that right? Or did I already forget it? Minus 1, 3, minus 2. Minus 1, 3, minus 2. Okay. Minus 1, 3, minus 2. Minus 1, 3, minus 2. Okay. Then I have dimensions of speed of light. C is speed. Speed is what? Distance divided by time. So it's 0, 1, minus 1. And then I have h. Okay, h is important. Planck's constant. I don't know if you have heard about this before, but this is where the quantum revolution had started in physics. Planck's constant. This is what quantizes everything really in physics. So Max Planck had said energy comes in quantas, in packets. And energy is given as h times f. We're talking about quantum world there. This is not the world that you and I see and we sense. This is a quantum world that's a very bizarre, very weird world that we can't even think about. It's beyond our wildest imaginations, actually. But math takes us there. Anyway, back to this. Energy is measured in joules. H, its SI units. Let's figure out its SI units. Frequency is 1 over seconds. So what do? Multiply both sides by seconds. Second cancels out. So SI unit of H is joules per second. Now, talking about the dimensional formula for H, let's figure it out. We know it's going to be energy times time. Energy is m1 L2 T minus 2, and time is m0 L0 T1. This gives us m1 L2 T minus 1. So 1, 2 minus 1. Dimensions of H. 1, 2 minus 1. Alrighty. We are told that the time period T depends on G, C, and H. What is this dependence? It's A, B, and C. And that's what we're trying to figure out. A, B, and C. What is this A? What is this B? And what is this C? So we're going to remove this symbol of proportionality and introduce a constant G. We're going to remove the symbol of proportionality and introduce a constant of proportionality, A, which is over here, this A. And this A is dimensionless and therefore unitless. All right, so let's go ahead and what we're going to do is, now our goal is to find out A, B, and C. On the left-hand side, we know that the dimensions are that of time. So on the right side as well, we should have dimensions of time. A is dimensionless, so let's not worry about its dimensions. G has dimensions of m minus 1, L3, T minus 2. I'm just writing it right out of here. Okay. And I'm going to raise this to the power A. Then I have B, which is, what the heck did I do? I'm going to remove this symbol of proportionality and introduce a constant A. This A is dimensionless and therefore unitless. Now, in terms of the dimensional formula, on the left-hand side, I got just time, m0, L0, and T1. A is dimensionless, so let's not worry about this. G, its dimensions are, here we got minus 1, 3, minus 2, m minus 1, L3, T minus 2 to the power A. Then I have C. C is m0, L1, T minus 1 to the power B. Then I have this H here. H is m1, L2, T minus 1 to the power C. All right, now let's go ahead and collect the factors with the same base on the right-hand side. What do we get? M to the power minus A. 0 times B is just 0. And here we have plus C coming from here. L, 3A B plus 2C. Then we have T minus 2A minus B minus C. Now we're going to solve for A, B, and C here. What do we get? M is the base here, M is the base. Then when the base is same, equate the power. So on the either side of the equation, when the base is same, you equate the power. So we get for M, 0 equals minus A plus C. For L, 0 equals 3A plus B plus 2C. For T, 1 equals minus 2A minus B minus C. So here now we have 3 equations, 3 unknowns. Can we solve it? Sure we can. But I'll show you in a few minutes that we could have solved the problem without doing all this. I'll show you how. This first equation gives us A equals C. So what I'll do is, in the second and the third equation, I'm going to replace C by A. 0 equals 3A plus B plus 2C. And this gives us 0, not 0, this is 1. I would like it to be 0. 1 equals minus 2A minus B minus blah, 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 blah. Let's call these equations A, B, and C. Now in B and C, I'm going to replace C by A. So that gives me 0 equals 3A plus B plus 2A. Third equation, which is C, becomes 1 equals minus 2A minus B minus A. Okay. Now with this, B becomes, I'm going to swap left and right just because 5A plus B equals 0, and I get minus 3A plus B equals 1. Okay. This is minus, this is minus, this is not plus. So if I just simply add these two equations, B's cancel out, I get 5 minus 3 equals 2A equals 1. This gives me A equals 1/2, which gives me that C also equals 1/2. Now I have A and C both. I can insert the value of A in either of these equations here and solve for B. So the dimensional formula of G is mass inverse length cubed time minus 2. You see that? From here. Kilograms comes upstairs, becomes minus 1. Meter cube stays upstairs, and second square comes upstairs, becomes negative 2. Okay. Now we might as well figure out the, okay, let me write it here. Minus 1, 3, minus 2. Dimensions of G. Minus 1, 2, minus 3. Is that right? Or did I already forget it? Minus 1, 3, minus 2. Minus 1, 3, minus 2. Okay. Minus 1, 3, minus 2. Minus 1, 3, minus 2. Okay. Then I have dimensions of speed of light. C is speed. Speed is what? Distance divided by time. So it's 0, 1, minus 1. And then I have h. Okay, h is important. Planck's constant. I don't know if you have heard about this before, but this is where the quantum revolution had started in physics. Planck's constant. This is what quantizes everything really in physics. So Max Planck had said energy comes in quantas, in packets. And energy is given as h times f. We're talking about quantum world there. This is not the world that you and I see and we sense. This is a quantum world that's a very bizarre, very weird world that we can't even think about. It's beyond our wildest imaginations, actually. But math takes us there. Anyway, back to this. Energy is measured in joules. H, its SI units. Let's figure out its SI units. Frequency is 1 over seconds. So what do? Multiply both sides by seconds. Second cancels out. So SI unit of H is joules per second. Now, talking about the dimensional formula for H, let's figure it out. We know it's going to be energy times time. Energy is m1 L2 T minus 2, and time is m0 L0 T1. This gives us m1 L2 T minus 1. So 1, 2 minus 1. Dimensions of H. 1, 2 minus 1. Alrighty. We are told that the time period T depends on G, C, and H. What is this dependence? It's A, B, and C. And that's what we're trying to figure out. A, B, and C. What is this A? What is this B? And what is this C? I'm going to remove this symbol of proportionality and introduce a constant A. This A is dimensionless and therefore unitless. Now, in terms of the dimensional formula, on the left-hand side, I got just time, M0, L0, and T1. A is dimensionless, so let's not worry about this. G, its dimensions are, here we got -1, 3, -2, M -1, L3, T -2 to the power A. Then I have C. C is M0, L1, T -1 to the power B. Then I have this H here. H is M1, L2, T -1 to the power C. All right, now let's go ahead and collect the factors with the same base on the right-hand side. What do we get? M to the power minus A. 0 times B is just 0. And here we have plus C coming from here. L, 3A B plus 2C. Then we have T, minus 2A minus B minus C. Now we're going to solve for A, B, and C here. What do we get? M is the base here, M is the base. Then when the base is same, equate the power. So on the either side of the equation, when the base is same, you equate the power. So we get for M, 0 equals minus A plus C. For L, 0 equals 3A plus B plus 2C. For T, 1 equals minus 2A minus B minus C. So here now we have 3 equations, 3 unknowns. Can we solve it? Sure we can. But I'll show you in a few minutes that we could have solved the problem without doing all this. I'll show you how. This first equation gives us A equals C. So what I'll do is, in the second and the third equation, I'm going to replace C by A. 0 equals 3A plus B plus 2C. And this gives us 0, not 0. Let's call these equations A, B, and C. Now in B and C, I'm going to replace C by A. So that gives me 0 equals 3A plus B plus 2A. Third equation, which is C, becomes 1 equals minus 2A minus B minus A. Okay. Now with this, B becomes, I'm going to swap left and right just because 5A plus B equals 0. and I get minus 3a plus b equals 1. Okay. This is minus, this is not plus. So if I just simply add these two equations, b's cancel out, I get 5 minus 3 equals 2a equals 1. This gives me a equals 1/2, which gives me that c also equals 1/2. Now I have a and c both. I can insert the value of a in either of these equations here and solve for b. So I know that 5a plus b equals 0. That means 5 times 1/2 plus b equals 0. So 5/2 plus b equals 0 means subtract minus 5/2 from both sides. That gives you b equals minus 5/2. So what was my equation? I wrote my equation as t equals a times g to the power a, c to the power b, and then I had h to the power c. I said a is equal to 1/2. So to solve it, if you're in a time crunch, how would you solve it? I would plug in the units of, or the, if you were in a time crunch, you can try putting in just the dimensions of time here. So g has time to the power minus 2, and h has to the power minus 1, divided by c. C is t to the power minus 1, but it's raised to the power 3. So you see that you get t to the power minus 3 divided by t to the power minus 3. They just cancel out. This will have no dimensions of time, no units of time. So A is incorrect. Same way for A, it's for this B here. C is t to the power minus 1 to the power 5. H, there's only one H. T to the power minus 1. G, t to the power minus 2. Sure, there's a square root on the outside, but look at this. You get